Hi everyone, we're going to do a week 3 quiz review. So in general, most people did pretty well on the quiz, but there were a few questions that some had issues with. So for most of the questions, more than 60% of the class answered correctly, but there were 4 questions that seemed to give some students some trouble. One was where the charged transfer RNA adds that amino acid. So you remember in translation, you have your messenger RNA, and let's say you have your different amino acids, and your ribosomes are coming in and they are going to read down the messenger RNA, and there is an A site and a P site. So the acceptor site is the first site. So when that transfer RNA grabs your amino acid, I'm not going to draw it correctly, but you have your transfer RNA, it's going to bring that transfer RNA into the A site. The ribosome is then going to move down to the next triplet codon. The A site is going to move and be over here now with your methionine there. And this becomes, what was the P site becomes the A site. This now is the P site. And so the next amino acid with transfer RNA gets deposited in the A site. And then the ribosome moves down. That A site where the amino acid is becomes the P site. And the next amino acid gets added in the A site. So A site is where your charged transfer RNA adds your amino acids in translation. Another question was how many reading frames. So again, if we're considering messenger RNA, we have to think about the different reading frames. So let's look at it this way. Here's one reading frame. AUG, GGG, GCG, CTC, TGA. Now, if you were to move by one nucleotide, then the next reading frame, this would be reading frame number 2, would actually be UGG, and then GGG, and then C, G, C, and then T, C, T, etc. And then the third reading frame would move down another another nucleotide, and that would be GGG, GGC, GCT, CTG. Now, if you were to move down another nucleotide, you'd then be at GGG, which is what you had in that first reading frame. So really, there are 3 reading frames per messenger RNA in translation. So if you have a 1 nucleotide deletion, your reading frame bounces over by 1 nucleotide. If you have a 3 nucleotide deletion, you're back at your original reading frame. It's just that you'd be missing that first amino acid. So there are 3 reading frames. Another question, you had to choose a correct statement about transcription. And just remember that RNA is always transcribed in the 5' to 3' direction. So in molecular biology, when in doubt, the answer is typically 5' to 3'. So RNA is always transcribed in the 5' to 3' direction. And that's why you actually have a leading strand and a lagging strand in recombination. So if you're considering your in replication, you have your 5' to 3' and your 3' to 5'. You have to make your template, your next strand, in the 5' to 3' direction. So this is why this original 3' to 5' strand is the leading strand, because you can make the corresponding strand in the 5' to 3' direction, and you could do that continuously. Whereas in the opposite strand, which is the lagging strand, because this strand is in the 5' to 3' direction already, you have to make your copy, your complementary strand, in fragments, these Okazaki fragments, because you have to make them in the 5' to 3' direction. So 5' to 3', that is how your RNA is transcribed. That's how your complementary DNA strands are added on in recombination, is 5' to 3'. Okay, the other question, which I'm going to be honest, I am disappointed that a lot of people answered this question incorrectly, and that is because we've gone over it several times. So in week 1, there was a DNA hint that went over this concept. It was gone over again it was put in again at week 2. In week 2, you had a question about this on the quiz, and so there was a review about it posted in the announcements and in week 3. And there was another question on it in the week 3 quiz. And again, many people answered this incorrectly. So if you have, this is complementary DNA. So if you have a DNA sequence that is 5' G, C, G, T, C, A, C, 3'. And I ask you what the complementary DNA sequence is. The first thing you want to do is, on your whiteboard, you would then write your complementary DNA. And I think everyone could do this very easily. 3', C, G, C, A, G, T, G, 5'. And some of you see this sequence, C, G, C, A, G, T, G, in the answers. But in the answers, they were all written in the 5' to 3' direction. So this cannot be the sequence, because this is 3' to 5'. So you have to actually look at the 5' to 3' direction, and in this case, if you read it this way, it's G, T, G, A, C, G, C. That is the correct answer for this question. So that's the concept. It shouldn't matter what nucleotide string I give you, if you have to consider the orientation. You can't just look at the sequence. If it's written in the 5' to 3' direction, you have to reverse that 3' to 5' sequence that you draw. There was a complementary RNA question, and most of you answered that question correctly. And the reason is that question was actually started in the 3' direction, and we can just make up a sequence here. and the answer was actually written in the correct orientation. So most of you answered this correctly because there was no need to change any orientation. So it was 5 prime, not that it was this sequence, but it doesn't matter what sequence it was, A, and so there's no T's in RNA, so you have to remember that that's a U, C, G, 3 prime. So everybody, most people answered that one correctly. It was the DNA question with the orientation that people continue to answer incorrectly, and that's an important concept. So if you're still not understanding it after this review, you should make an appointment and we can meet through the computer and I can go over this in more detail. So this is our review for the week 3 quiz, and we will continue to do these each week for questions that people seem to be having issues with. Okay, thanks.